Okay, great. So let's get started. So I suppose I could start with this doc here. I want to see what is the first thing because they are related. So we're probably going to jump back and forth to both because they kind of move in the same order. So what are we going to cover today? First, we're going to understand what this question is or need is for persistence in data and what that word persistence means. Second, we're going to explain the structure of a relational database. So PostgreSQL is a kind of database. And it's only one kind. There is another big kind, and then there are more kinds than that. But we're going to basically be keeping our conversation in relational databases, which PSQL is one of them. And we'll only talk about the other ones in relation to, well, it's different and you don't need to know much about it. Okay. We're going to talk a little bit about installing and managing a PostgreSQL environment on your local machine, which some of you already have that set up, but we can help you otherwise. And then finally, the idea of creating and then querying a database using SQL commands. So we'll get into all that if there's terms there that don't make sense, but yeah. So the first thing is persistence. So can anyone give me a good definition of what persistence means? Just as an English word, not even as a computer science thing, just what is persistence?
Like you keep doing it.
What was that?
Like you keep doing it, like day after day, like it's just like on schedule. You're just keeping the same thing going.
Yeah, exactly. Yeah. So persistence can mean like effort in a human being where, if you're trying to like run a marathon, you might have to practice running. And so you would want to be persistent in that running practice. So when we use it in a computer science where we're using it in a relatively similar sense, but we're saying persistence not meaning like an ongoing effort, but more of just the fact that it lives on from day to day. So when you turn on your computer and you're running a program, all the information of the program you're running is happening in memory, but memory is not persistent. When you turn your computer off, when it loses power, whatever you were doing on the computer, whatever, sort of local variables existed in that program you were running, unless you saved it, it doesn't exist anymore. Because memory is not persistent. Hard drives, on the other hand, are persistent in the sense that if you once you save something to your hard drive, if you were to unplug your computer and then plug it back in, even with the loss of power, that data still exists. It persists. And databases as a whole are the field of asking the question, if we have data that we want to persist, that we want to store and store and store in this, database, and then we come back to it a day later, a week later, a month later, a year later, however long later, we want that data to still exist in exactly, the form it was stored in. So databases are almost like they're a domain of computer science that realize there's kind of a very narrow desire for this thing called a database, which is, we might want it to be fast, but at the very least, we want to be able to store things in the database. We want to be able to retrieve things from the database. And importantly, we want to make sure that, we might get into this a little bit, but what makes one, like every database will let you store things and retrieve things, and every database will try and do that as efficiently as possible. But different databases have different guarantees of things like essentially a little hard to get into, but different databases can take different strategies, just like different data structures can take different strategies to saying what will be efficient on average, what won't be efficient on average, and what are certain guarantees you might get because things are done a certain way. But the important point is that a database is kind of like this solved system that you learn about, and you learn about how to interact with it with this, language called SQL. But you never really learn how the internals work, and you're not supposed to. A database is just supposed to be a kind of black box that you can talk to through SQL, but you don't have to have any sense of how data is actually stored in it. But before really diving into databases, something we can ask ourselves, which we should ask ourselves all the time when adding a new technology, is there a simpler option available? Do we really need this? Because it could be that we already know enough that we can get away without this new concept or this new technology. So the answer might be right in front of you, but if I were to tell you, hey, there's a bunch of data that you want to save, you want it to persist between, sessions of whatever you're doing with your program, what's a solution you might come up with what you already know, not involving a database? How might you save data so that it can persist between, times that you're using that data?
To some kind of file.
Exactly right. So that's what a file is. And when you've been using those CSV files, that's exactly what that is. As in, CSV is just essentially a data format for storing data. And JSON, which we've seen a little bit of perhaps, is a JavaScript-based equivalent sort of data format. So over here, we see like, okay, well, we have a data folder and it has these 3 JSON files, whatever they represent. And then we can look at it, and each file might contain, a specific student's school record. So they're going to have different, key value pairs, first name Megan, last name Remy. And it looks like everything is either a string or some kind of complex data type that contains a string. So we see like birth date is just a string, but address is an object that contains a bunch of fields, which each contain a string, and then classes is an array that contains a bunch of strings. So we're already seeing that, JSON allows us to support a couple of different data types, and it can store the information. And when it's stored, it's just stored as a plain file. So this example is given here. I think it's a little much, but basically this is saying like, well, if you were using JSON as your way of storing data, how might you interact with that file? And basically what you would have to do is read all of the relevant files and somehow combine them into like a single object that you can query for the information. And because we don't have any unique knowledge about this, the nature of the JSON we hold, it's difficult to make any sort of guarantees about what is slow or fast. So it's just an object by the time we turn it into code. And if we were to look through this, we might say like, well, if we want to get someone's address or something, we might have to take all of our pieces of data, which are just going to be some kind of like list maybe. And then we'll have to look through each one of them for, let's say, the first name and last name that matches. And once we find that, we know we found the right person. And then we'll say, okay, we'll grab their address, and then that's going to be an object. Then we'll say, we'll grab the state, and then that's a specific thing, and now we have it. But basically, it's if you were to solve the persistence problem with documents, you would have something like this, where you essentially have individual documents representing data, and then it's you, the programmer's responsibility to sort of collate all that data and organize it in some way that makes it easier or more efficient to, quickly get the data you care about. So this section is just kind of saying to us, okay, well, as we see that we have our data in this certain format, and we have this file here that sort of, turns that data into something Python will understand, and then you can manipulate it. But this is just asking some questions about like what happens if our use case grows. So what happens if we want to find a student record by name instead of ID number? I guess we were originally just looking at it by ID number. And then we might have the question, what if we wanted to just instantly grab all the students enrolled in a particular course? So you see here, each student has a course or various classes. So what if I wanted to say like, give me all the students that ever took History 107? If we just have it in this normal JSON way, I would basically have to look through every single record and then filter them out to just grab the records that have history 107 as part of the classes. And then maybe I would take all those records and say, just give me the first and last name of each person. And then again, like another strange one, like finding the number of students whose birthday is in the next month. So as we can see, we kind of have we have data, and we store that data in a certain way, but that's not everything. As in, a database should not just consist of the fact that you're able to store and retrieve the data in a basic sense, like saying, okay, store all these things, and each one I store is going to have like an ID associated with it. And then when I give you that ID, you give me that one back. But rather, a database ideally should have some kind of interface in which we could say what sort of data we want. So we're storing all that data, but what if we wanted to say, hey, I'm looking for just the number of students whose birthday is in the next month? That's kind of a complex query. And if we were to do it manually, it would take a fair amount of effort and require us to really understand how we're, storing our data. So I don't know that it's so clear based on what you've seen, but the goal of showing this was to inspire you to feel like, hey, individual files might not be a good approach after a certain amount of time. And there's really two reasons for that. One would be, or two essential reasons would be, one, you want your, you want to have an abstraction between your database and how it is saved, in the sense that ideally your database is not, one gigantic file or lots of little files that you understand. Your database should be essentially a program that it worries about how it stores things, what file it stores it in. But that database program handles the storing of data. And then also it handles the retrieving of data such that you can ask it more specific questions than just give me record 1, give me record 44. You want to be able to say, hey, database, can you quickly crunch the numbers and just tell me all the students whose birthdays are in the next month? And actually, I don't care about the specific students. I just want to know the number of them. So databases are designed to not just store all the data, but to give you a way of querying the data that is natural and lets you sort of ask big questions of the data without having to get into the details of how that data is actually stored. So everything I just talked about describes all databases. Databases are just a system by which we save and store and retrieve data. But there's one type of database that really became sort of like the central approach for most people. So you might have heard of SQL databases and NoSQL databases. We're not going to get too much into what a NoSQL database is yet, but a SQL database is what PostgreSQL is. And it's an example of this thing that we would call an RDBMS, or a relational database management system, which is a very long term, but the important word there is just the R, relational. So what does that mean exactly? Well, looking through some of this stuff, I just want to see, we have future users of large things. So there's some stuff here about how I mean, I think some of this is a little too specific. Just some guarantees that the database system might want to provide. But as I see it, an important part about a relational database is first that we're going to have this concept of a schema. So just like when you were making objects, an object was like a blueprint, right? And then you made individual instances of that, or sorry, a class was like a blueprint. And then you made individual instances of that class, which were objects, and that represented the actual data, whereas the class represented a blueprint for something of that kind. So a relational database uses a similar system, but what instead of a class, we have this thing called a schema, and a schema defines what the shape of your database is, what the shape of your table is, as we say. So a database, or a relational database rather, can have multiple tables. Tables are kind of the top level thing that organizes everything. So I might say, okay, well, I have a student table, and every student has an ID of first name, last name, birth date, address ID. And then I might have an address. An address has all this data. And then I might have classes meaning like up here when we saw these, history 107, CS 101. And then a class might have, has an ID, name, credit, enrollments, ID, student ID, class ID, grade. So just looking at this, can you tell me first, what is something that virtually everything in here seems to have? I see addresses doesn't have it, but it should.
An ID.
Yes, exactly. So I'm going to quickly update that. Address should have an ID because everything in a relational database should have an ID. And that brings us to the second question of why should everything have an ID? So notice that if I'm looking at students, a student has an ID, has a first name, last name, birth date, address ID. So what do we think address ID refers to here?
The ID and the address table.
Exactly. So when you see something like address underscore ID, or let's see another student underscore ID, class underscore ID, that's the main reason relational databases exist, because we would call that a foreign key. So this ID is the main key. So if I want to get student number 4, I say, okay, I'm looking for a student with ID number 4. But then I would look at student ID number 4, and he might have an address ID here of 8. And then I would say, oh, well, an address ID of 8, that means I want to look in the addresses table and look for the 8th thing, or the thing with the ID of 8. So when you look at this model up here with JSON, its biggest problem is that everything is a single object. And so let's say 10, I mean, this is a little silly, but let's say 10 students all shared the same address, right? Well, each one of their files would have a unique address here, and they would just all have copies of the same thing. And similarly, if we wanted to change, the address that everyone shared, let's say this address was like, Code Platoon's WeWork address. So like lots of students share this address. We'd have to change it in each one of those documents that represents the individual students. But in this relational approach, we might have, 20 students, and they all have an address ID of 7. And let's say we wanted to update that address. Well, then we just look at our addresses. We find address 7. We don't change anything about the students. And we say, okay, well, address 7 now has a new value at it. But everything that pointed to it in terms of its address ID can still remain pointing at it. It's just, it now holds a new value. So relational, the idea of relational databases is predominantly about sharing or not repeating yourself, because anytime you have a large chunk of data, it doesn't live within, the address doesn't live within the student's table. Rather, the address, there's an addresses table, and a given student can just have an address ID that points to that address, that specific addresses thing. So that's sort of a lot, but let's stop for questions, and then we'll probably go to the slides for a little bit.
Just out of curiosity, so barring how to actually use it, since I don't know how, is the database layout, is that something that you're taught whenever you kind of, like, if you're going to be managing the back end? Is there some kind of like README that's usually given to you, or is that kind of through InDoc? Just kind of general work question.
So ideally, like, remember in the past when I showed you those, what are they called again? Those class-based documents that sort of tell you what something looks like. What are those called again? The object documents.
UML docs.
Yeah, so let's look at a UML doc real quickly. And you can kind of see how UML docs are not too different from like schemas. So this is what a UML doc looks like. And it's pretty complex, but it's telling you like, here's a bunch of objects, now they're related to each other, and who has access to or owns what, and who is a, who inherits from what. And then if I said schema or SQL schema, let's see if we can get an example. Same thing, exactly. So ideally, your company will have something like this, which says like, okay, well, this is our system. We have bookings. I don't know what these mean exactly, but I think the way it works is it's saying like, okay, a booking menu item contains one booking. A booking contains possibly multiple menus, multiple chefs. A menu contains multiple menu courses. And you see that these are all related by ID. So like a booking menu item has a booking ID, and that's going to relate to this. They have these little keys next to it to say, okay, well, this is the primary key. So a booking ID is what goes inside of booking underscore ID. Similarly, a menu's ID could go in menu underscore ID. And this is essentially what a database schema is. And as you'll notice, they have the actual, they have some data types here, which is useful. This right here where it says chef ID int question mark, that question mark likely means it might exist or it might just be null. So that's an ID that will come up again. But to answer your question, if you didn't have access to something like this, any system like PSQL should have, it's not going to be easy for me to show it because I have nothing on there right now, but it should have some commands in there. So if I look here, PostgreSQL, I could say \help, and it's going to give me way too many things. So maybe I'll just say / and that, \question mark. And in here, it's not an amazing way to see, but basically I want to say, show me all of my, show me everything that's in the database. There must be a way to do that. And it's usually /d. And let's see, do I have a great, I'm not saying just basic /d, but /d will show you all the tables in that given database. So if I type / or it's a little hard for me to see with everything covering my screen. So I'm going to quit out of that. And then I'm going to type /d. It doesn't find anything because I'm currently because I just installed this. But no matter how many tables I add to it, that /d will eventually tell me all of my tables. And then there's other useful, like you saw, there's lots of commands you can possibly give it that will allow you to, walk through the database and find out all the information you need if you didn't have an image like that. Yeah. Cool. So anything else in terms of basic questions before we not move on, but really just redo that basic information in the slides? So my goal is before we even discuss this idea of SQL, which is, the actual querying of data, we want to understand what a database is. Okay, cool. Well, if we don't have any more questions, we'll go to the slides for a second here. So this is meant to just show you that there's essentially two kinds of databases, relational and non-relational. And relational here has these connections where it's going to use an ID, which is like a reference. It's just going to hold a number. It's going to use an ID to refer to something else in another table. And you just have these multiple tables, and they can, so like product here represents a table, and there could be, 10 individual products and maybe, 1,000 individual customers. But this box here just represents an entire table, not an individual entry in that table. And then these lines represent how you can use the fields in your schema to say, well, this is a foreign key, and that foreign key relates to the product table or it relates to the order table. And that way, everything is tied together. You don't have to repeat yourself as much, and it's a lot easier to say like, give me all the products that are currently on the order line, whatever that means. You can easily say like, okay, go through everything in the order line, everything with product ID, grab that product and give me its name and price or something. And by comparison, we see this thing over here, this non-relational database. A non-relational database is essentially a JavaScript object. It's an object that can contain other objects and at some point are going to terminate in primitive values like 56 or, you know, this string I or something. And a non-relational database is like an object in that it's really easy to get started with it. And importantly, it can contain anything. So it doesn't have this need of a relational database where you define a schema first. You could just define new fields and values as you go with a non-relational database. But the problem is that because you don't have that relational aspect, it becomes very, like, let's say you're trying to invent Facebook, right? Facebook might have, in the relational world, Facebook might have a table called users, right? And each user will have a field, a field called ID, and that'll have their own ID. And then they'll also probably have a field called friends. And that friends field might be a list, and that list would be a list of IDs that represent other users of the platform. And so that's a reasonable approach to creating essentially a graph of users. Whereas if you look at the non-relational approach, how would you do that? As in, you might have one person, right? And you're going to start representing him, and you give him an ID and a name and some things. And then you say, okay, here are his friends, and there's a list. But you got to fill out each one of those individual friends, and they themselves have a list of friends. So you actually can't do it, as far as I know. You can't represent something that involves lots of relationships in a non-relational database. And so non-relational database is just not a good fit for data that involves lots of connections. It's a perfectly fine fit if you're just trying to store lots of data. But it doesn't capture that relational aspect. So, right, we mentioned this a little before, the two halves of a relational database. On the one hand, you're going to have the storage mechanism. In this case, because it's a relational database, we have this idea of tables, and tables have columns and rows. So maybe that's worth showing, because right now we're just looking at the schema level. So if I were to look at, if I were to put this in Excalidraw, let's say, Excalidraw, and I want a new thing in Excalidraw. Can I do that? Just get rid of everything Excalidraw. I guess I can't. I'm just going to scroll down to where I don't have anything anymore. Okay, so I can start writing here. And let me look at what was that. So let's say we wanted to say, like, we were representing students, right? First name, last name, birth date. Let me just, or let's just say we're starting with our simplest possible database schema. So I'm going to create a new table, and I'm calling the table students, right? That's what I'm referring to this whole table as. And then I said, based on my schema, that a student has ID, first name, last name, birth date, address ID. So if I were to add a new student, because it's a table, we essentially get a new row. A row represents an individual student. But notably, these rows have, so this is my students table, and maybe over here I'll write table is students. And then over here we have our columns. And our columns represent our schema. They represent the individual values that the individual fields that each student cares about. So looks like we have, if I were to start, it's almost like I want to, you'll see it makes more sense to do something like this. So I'm going to want to copy that over a couple times, but first we have my ID. And then what were the other ones I had? I don't even need to give all of them. I'll just give a first name. These are too big, obviously. Let's do something like that. So first name. Last name, and what was other stuff it had? Okay, birth date and address ID. That's enough. birth date and address ID. Cool. Kind of mixing my approach here. It looks like SQL prefers that everything would be like that or something. Just a convention doesn't actually matter, but I like to keep conventions like, okay, so if I'm going to have something like this, let's copy some of these lines here. And when this is done, we have a table. So basically, this is our entire table representing, maybe I'll put a line here. This is our table that represents students. And now let's say I wanted to add a new student, right? Well, I would create a new row. And when I create a new row, I'm going to say, okay, well, this student is my first student. Let's give them an ID of 0. Doesn't actually matter what the ID is as long as it's unique. Every student has to have a totally unique ID because that ID is how we know that's who that is. And then maybe this student would be, say, Delgado, just because I see him on the screen. And the birth date. Okay, so first of all, what are these actually being saved as? This is a number, but it looks like first name is a string. And importantly, part of the way that this works, if we were to define the schema, we would have to say, okay, first name holds a string. And we couldn't then later give a first name of 1. We would say every student has a first name, and that first name must be a string. So you can't have, maybe you would say you can't have an empty string, you can't have this, you can't have that, but the type is sort of built in and enforced. So it's sort of like languages with static typing. So unlike Python or JavaScript, you have to be explicit about the type and you can't just switch it up on the fly. So similarly, birth date might be a string. And we would make it a string that looks like, 02, 08. Jose's probably very old. So let's say 1942 or something. That seems appropriate. Okay.
Man,
Is that right? Did I get it exactly?
tell me how you really feel, Ben.
Well, I don't know. I'm just assuming you're 81.
Tell me how you really feel, Ben.
I don't know. I mean, this is how I feel. This is how I feel. 1942.
We're getting out there.
Okay, so right. So this is almost a complete student. But maybe here we say like, well, actually, he's related to address ID 1. And then what would that mean? Well, that would mean that, separately, we have, maybe I'll make this a little shorter so that, never mind. I won't make it shorter. Separately, I have this table called address, right? So I'm going to copy this and put it here. Just get rid of these two. So imagine I have this this table called address, and an address is different than a student. It has an ID, line 1, city, state, zip code. So ID, line 1, city, state, zip code. Okay, and I said, okay, well, this is an address with ID 1. So over here in ID, this 1 will now refer to this address, and this address would be, whatever it was, 123 Main Street, city will be LA. We're just guessing. State will be California. Again, it would be a string. So let's be explicit. And then finally, a zip code. Maybe we do just represent that as a number. We probably would represent it as a string because we don't care about it as a number. Here's the zip code. And so the core idea of a relational database is that we're going to add, 1, 2, 3. We're going to add as many students as we want. So I could, have another student here and whatever. We just have data in here. I don't even have to write that, whatever. We have some data in here, but importantly, they could both share the same address if they wanted, if two people live together, or there could be a brand new address. It could be 44. And then I would have some entry in addresses that's 44. But the core idea is just that the the core idea is that you have columns that represent, you have a table that represents all the students. You have columns that represent the schema or the data that the shape of the data each student must fit. Each row represents a given student in the student's column. And then one of the columns or many of the columns could contain what we would call a foreign key. So we must have a primary key, which represents who the student is, but then there could be a foreign key like address ID, which represents a key in another table. So in this case, the address ID represents the address table, and similarly, that has its own entries. So once again, that's a fair amount of information. So let's stop for a second and just ask, how do we feel about this, this general conception of relational databases and tables?
Could you go over again, like the main key and the foreign key concept, like the difference between those two?
Yeah, we'll definitely get into it more eventually because it's one of the core ideas, but essentially everything will have an ID or a primary key. The primary key is generally just called ID, and it represents that thing. So if you were to say, give me the student with ID 1, we would look at this student with ID 0, this student with ID 44, some student down here. But if I look at an individual student, there's no reason it can't have any sort of column. It can't have any sort of, column. And so one thing a column can hold a string or a number, but just like in an object, right? You can hold a reference to something else. So, and that reference is just a memory address. So in a table, you can have a column called address ID, and we would call that a foreign key. And it's called foreign because this is the primary key, which we only have one of, and we must have it. But we can have one or many foreign keys in a database, and it's just pointing you to some other table and the ID to care about at that table. So address ID 1 tells you, okay, well, look at the address table, find the ID with 1. And the way you might think about it is like, if you wanted to get all of the data for a given student, you might say, okay, like your algorithm, if you like the database usually does this for you, but the algorithm might look like, for get total student record, it would almost look like something like, okay, I would say student, I would say maybe something like student equal, I mean, this is very much pseudocode, but I'm saying like something like student dot equals get student, and then I'm going to give it the ID of 1 or something, or maybe that was passed in, right? So I'm gonna grab the ID is going to be an input, but I'm gonna say, okay, get the student with get student ID, and then because I know how a student is formatted, I could say, well, student has a foreign key on it, right, called address, and then I might say student's address equals get address. So that's going to look something up from the addresses table. And what does it take as its ID? Well, we already have our student, so we're going to say student dot address underscore ID. So let's move that over a bit. This is not something you'll actually ever write, but I just want to show you what pseudocode might look like for a database in which you're basically like, this is the whole point of a foreign key, that you can use it to then get more data. Does that make sense?
Yes, thank you.
All right, cool. Any more questions about what we've
Yeah, I
covered?
have a question.
Yeah.
So when you have, for example, an address that's related to multiple students, so multiple students have the same address, and let's say it's address 1, you have 5 students with address ID of 1. If one of those students changes address, so obviously you don't want to change the address for all 5 students. Is SQL going to make, or is it first going to is this something, I guess, automatic, or do we have to make it do all this? Do you go and check the new address and see if there's any record of it already, and then append that new address ID to the student, or you just create a new one? And
Yeah.
then,
That's a really good question. You as the person who has access to the database could choose, but essentially, it sounds like you're saying like, okay, so I have, let's say I had multiple, we're not going to worry about the values on it too much, but let's say I had these 4 users, right? Just assume they had different first names, different last names, whatever. They're 4 unique users, and you're saying they all point to the same address, right?
right, and we want to change student 2's address to something different.
Yeah, so let's say you just wanted to change student 2's address. What you would do is say, okay, well, student 2 now points to a different address. Well, does this address exist already that you're talking about, or it's new?
I don't know. That's the question is, does it have to go through the entire database and check if it exists?
If we wanted to check if it already exists, yes, it would have to go through the whole database. And ideally, there would be a way to do that well. As in, you're saying we only have the ID. How are we going to find out if something is a matching database, or sorry, a matching address entry? That's more a technical question of like, how might you do a quick lookup? And there are, relational databases have a method of doing quicker lookup when you know what you're looking for besides ID. But let's say we knew it wasn't in the database. What we would do at that point is say, okay, well, let's make a new address.
Yeah, I mean, I get that bit.
Okay,
Make
fine,
a look and then reference that new ID. I was just thinking like, because you don't know whether or not another student 100,000 rows down the list has the same address that this guy is changing it to. And so you have to loop through 100,000 students.
Yes, exactly.
Comparing each bit of data to see if it's the same.
Yeah. So it's somewhat of an advanced topic, but we will eventually get to it. But what you're describing is what's called, I'm forgetting the phrase for it right now, but basically, databases by default have this idea of an ID, and as a result, they have random access to jump to that ID, right? Well, let's say you knew that you wanted to check an address by like line 1, city and state and zip code, just as one individual string, right? You could use this tool, which I'm forgetting about, but what it lets you do is pre-compute ahead of time, essentially a key that represents, like it's going to use hashing to say, okay, well, if you want to make sure
I was just about to ask you if you would make like a hash map.
Exactly. Yeah. So the solution on some level is definitely a hash map, but the important thing is that you never have to do it yourself because that idea is kind of built into a database. So I'm trying to remember what it's called again, but like this exists in databases to say pre-compute a means of hashing and ordering things so that I can more quickly look up things that are not looked up by ID. So it does exist, yeah. But we will not get to that right away. Cool. Any other questions about just what we've covered? Which I would say what we've covered so far is there's such a thing as a relational database versus a non-relational database. And relational databases have these 3 ideas, which are, or a few ideas, which are tables, schemas, columns, and rows. Okay, it seems like we're in a pretty good place. So I'm just going to keep going with this. So we have mentioned the storage mechanism. The thing we haven't mentioned yet, which is the other half of a relational database, which is this idea of querying the database. So there's this idea called SQL, and PostgreSQL is a specific type of SQL database. SQL being a type of relational database, but then you also have MySQL or SQLite or any or MS SQL or something. There's lots of SQL databases. So what is SQL? SQL stands for structured query language. So because you don't have to worry about the implementation of like, how do you actually store things? Similarly, you don't have to know how it's stored in order to retrieve it. Instead, you have this language essentially that defines how you might retrieve data, and then the SQL database, whatever it is, knows how to read that SQL and most efficiently get that data for you. So let's see, do we have an example on the next slide? Well, first, I guess, I believe we'll get to that example pretty soon, but we have this table, right? This table has ID, first name, last name, on probation. Whoa. For students, and we just have 2 in here. And then, right, this represents the table. That's an individual column. That's a row. And then the schema represents, I thought we would see SQL already, but the schema represents how that table might be formed. So this is already getting a little too much into the weeds, but basically what I wanted to show you is that SQL is a way of querying for the data you want. So let's say you had this list of students and you wanted to get the last name of all students. This is going to be pseudocode. I don't remember my SQL syntax exactly. Maybe someone can correct me. But I might say something. Or does anyone here know enough SQL yet to say, how might I write the SQL statement that would get me the last name of all the students? I might
select all, so select star from from table with last name.
It's with.
Let me make sure.
I think I might just
I thought
want
it was just select last name from.
Yeah,
student.
exactly. It's just
Oh,
select
yeah.
last name. Yeah.
Yeah.
So exactly. So this would be a SQL statement. So SQL would be this sort of, just like you have a programming language, it's a specific, unambiguous language that lets you talk to your database. So we would generally select when something is a SQL keyword, for whatever reason, we generally make it all caps. It doesn't have to be. SQL doesn't care. But that's just a thing to distinguish the keywords from the name of your table or the name of your column or something. So here we're saying select. Select meaning I want things from the database as opposed to I'm trying to update the database. So what do I want to select? Can be confusing to read it in order, but we're going to ignore this part first. So ignore last name. We'll just put a star here. And select star means select everything. And then select everything from what? Select everything from, and then you give it a specific table, the table students. So what this would return would be a list containing all of the students and all of their information. And yet over here, I could get specific and say, well, actually, I want to get just the last name of every student. And then that would give me a list containing, it's not telling me anything about the ID of the student anymore, but just their last name. And let's say I wanted more information, but not all the information. I could write something like this, where I say, for the entire students table, get me every student, but specifically get me just their ID and their last name. And then there's even more things where I could say, like, I'm forgetting exactly the language, but you can give it conditionals where you can say
You would say like where ID equals something.
exactly, yeah. So I might say select I want the ID and the last name of every student from the students table, but I want to limit it to saying only students whose, let's say, it's a little like only students whose birth date, I can't write this simply, but basically, eventually you could say like where that student's birth date. So I might be getting the syntax not perfectly right, but I want to say like where birth date like less than or equal to some value that it can understand, like, February 10th. So that's like a little bit of pseudo SQL in that you probably couldn't write it like this, where you said, you know, only if their birth date is less than or equal to February 10th, you know, 1998 or something. But this is the essential point, that like you can reference a table, you can say what columns you actually care about to grab from the table, and then you can add conditionals to say, actually, based on the data, I only want to take certain things. So it kind of gives you like filtering right in there, and sorting, and a bunch of other things that you would care about on data. So I feel like let's see, we've gone, maybe we'll take some more questions, but we're going to give you a break in 7 minutes. I just want to make sure that the beginning part is really solid, because it's kind of the hardest part to grok. Everything else eventually becomes like learning how to, you know, learning how to make a SQL statement, or learning how to add or remove tables or things like that. But in terms of the idea part, this is the idea. So this would be an example of, you know, select all students from the students table where the last name equals Garbus. And then they get more complex, but we're not going to get into those complex ones yet. So any questions? So yeah, I don't know that this is official SQL, or that this is a little bit of pseudocode. But as you could see, SQL also contains some like helper functions like count. So select count star will actually not return all the elements, rather it will return the count of all the elements. So this is going to say, tell me the number of total students in the students table whose birth dates are greater than, you know, January 1st, 2017, but less than January 30th, 2017. So basically tell me everyone who was born, tell me all the students who were born January 2017, how many of them there are. So like the core point of SQL is that you could write statements like this, where you don't have to worry about how the students table is really organized. But you're able to have this powerful query language where you can say, I care about this very specific question. Can you give me an answer in one line? All right, well, I'm going to keep the room open for questions for a second and look through some of this stuff, but it looks like we have not too much left. Really, we just need to start talking about SQL. In my opinion, this one right here is a little complex. We might be showing it to you, but we don't explain how it works yet. But this is this idea of joining is a core idea which lets you essentially join. Like over here, you have your students, and that student might have an individual address. So join is a way of saying, well, actually, I don't want a students table. I really want a table that has the students table joined to the address table, and the join happens on that foreign key. So when I join them, I'll end up with a student with a table that has all the attributes of a student, but then it also has all the attributes of an address. It has simply replaced address ID with all the attributes of the address relevant to that ID, if that makes sense. But if it doesn't, we'll get to the idea of joining tomorrow, I believe. Yeah, but any more questions in the next few minutes? Otherwise, we will come back. When we come back, we will do more of this this lecture, which I see we have a lot of slides of. And in here, we'll discuss schema, which represents essentially the plan or the class for that table, what data is supposed to look like, and what counts as valid or not valid data. We'll discuss how to actually create things in PSQL. What else is there to discuss? Yeah, we're basically going to be talking about schemas and how to design them. And let's see if we ever get to queries. We do. Queries would be not just creating the data, but now how you interact with it, select, insert, update, delete. And yeah, we will get into all that. But for the rest of the day, we're basically just talking about how you use PSQL practically to create tables, add things to them, manipulate what's in the table, and eventually we will get into having that interact with like Python or JavaScript in the sense of, you want to be able to programmatically mess with your SQL database. But for the beginning, we will just be writing everything raw into our SQL database. Cool. So yeah, let's give everyone a break and come back. Actually, you know what? Before I give you that break, I'll look at the chat quick to see if there's anything important.
Yeah, Ben, I've had a question actually.
Okay.
So it like the PSQL or SQLite or whatever, is that sort of just like an IDE for the databases? Or if you make a database in SQLite, can you not then load it or use it or query it through PSQL?
Yeah, I think it's more of the latter than the former, as in, we'll discuss this more when we get to the schema part of it, but essentially like, so SQL is the one common thing. They're all going to know SQL as a language to talk about the data and manipulate it. But MySQL, SQLite, Postgres, they all are different implementations. And so they might store things differently. They might practically do things differently. And an important part of that is that I'm not sure how many data types SQLite contains, but Postgres contains a lot. So if I said Postgres data types, I built in have like monetary types, for example. I could say money is a type, and it's going to understand that and be able to work with that in a way that SQLite, because of that light, probably doesn't have this specific data type. So if you tried to move your table from PostgreSQL to SQLite, it would complain, hey, you're using a data type that I've never heard of because I only understand like integers. So that's the main.
That makes sense.
Yeah, exactly. Yeah. So they're not quite transferable. Though it's usually possible to like take your whole Postgres database and do some kind of sanitization type like thing where basically you just have a program run through it and say, okay, anytime we see this, this list of things that it doesn't understand, replace it with something like int or something. Yeah. Any other questions about that? Otherwise, you know what? We're a minute over. You're getting your break now, and we're going to come back at what will be 10:15 for you. How about? And then we'll go to 11. I'm actually going to check. What is our, I get confused between my calendar, your calendar. So, okay, it looks like we have 2 hours left maximum. Well, maybe we'll try and break it up if it's that long. We'll see. Or we'll just give you lots of breaks. But yeah, I'll be back. You'll be back 10:15 CST. Just share everything again. Cool. Cool. So we have a fair amount of time left to go through some of this lecture content and just make sure that we understand SQL a little more than we currently do. So where were we? I guess we were here. So first, before we move on, is there anything from before? Does anyone have any lingering questions? Or I'm always trying to get a sense of how you guys actually feel, because I don't want to just be talking and no one's following. That's not so useful. So any questions to sort of solidify what we have so far before moving on? Okay, fair enough. Well, as we said, we have, tables. This represents the whole student table. ID here, as a column represents a column, just the IDs of all the students. And then a row would represent all of the data for one specific student. So the ID, first name, last name on probation, but just for that one row. And now we get to the idea of schemas. So a schema is essentially a blueprint for your table. It tells you what the shape of your data needs to be in order to be a valid entry into the table. So eventually we're going to add elements into our table. And in order for that to work, there needs to be an understanding of what shape the data is. So unlike with a JavaScript object or a Python object, a JavaScript or a Python object allows you to simply change what it looks like over time. So you might have some fields and then you'll say, well, actually, I want to add a field to that. And you can do that easily with an object, but with a table, you have to be very explicit about what actually fits. So our schema defines three things. It describes the name of the table, which is obvious that, you just like a class needs a name, you need to give the table a name. Otherwise, how do you refer to it? And then your columns have names. So your columns represent what specific fields this table holds for an individual row of data. And then each one of those columns has a type. So you can't just put anything in that column. You have to be explicit about what type it holds. So let's start to see some examples. I guess in order to do this, it might be wise to create a table. So here I am in PostgreSQL. It should understand SQL. You see there's that semicolon at the end, so usually I have to do that. But the first thing I might do is create a table. So let me create two tables. I'm creating a table. So create and table are both keywords there. And then I want to name my table students, and then there's a ... here because I believe it's not going to let me create it unless I provide some kind of schema. So I'll just try this now. What happens? Syntax error at or near clear, line 1 clear. I really don't know what that means, to be honest. But we will find out pretty soon. So I guess they're just saying by default, you want to give it lowercase plural noun names. So that's I don't think SQL actually, or PostgreSQL actually cares. You can name a table anything, but this is just a convention. And it makes sense that it would be plural because you are generally going to always be representing some kind of plural. So here's some examples. If you're storing people, maybe you would call it persons or peoples. I don't know. Purchase order, purchase underscore orders, liking a post, maybe you call that likes. I really think you get to choose this for yourself. You don't have to follow our rules of what good table names are. They're just suggestions. Okay, so here's an example of how I might actually create that first table. So as we mentioned, we got to give it a schema. And the way SQL is going to work is it's going to say, well, after you say the name of your table, I want you to define what is in a table. And notice that I was able to do open parentheses and hit enter. And now this prompt looks a little different. It knows that I'm continuing on the same statement. So the first thing I'm going to give it is an ID. Every student is going to have an ID. And that ID is going to have a type, and that type is going to be integer. So I can't tell you what all the types Postgres supports are. If we go to that website, you'll see that Postgres supports a fair amount of types. So Postgres data types. It really does, have so many types. Even with numeric, you get very specific about what the type means. You can store geometry in a smart way. There's date and time has very specific types. So Postgres, what makes it unique among the other, or one of the things that makes it unique among the other types of SQL databases is that it has all these different types that get very specific that can make it easy to store, let's say, JSON. It already knows about JSON. Or we're trying to support, store a polygon. Maybe our database is storing a lot of 3D models or, time in various ways. And so it supports lots and lots of these types, and you're not necessarily going to know all of them up front, but one of them is integer. And what we're saying there is that the ID has to be a number. Maybe I could dig in and find out exactly what an integer consists of, because it's going to have specific rules. It would seem like an integer. Yeah, basically, there's a lot of things to consider, and you often won't know all the details, but we're just going to go with integer, which I'm assuming means I can store a number, and there probably is a limit to how big that number can get, but for now, that should be fine. And then I'm going to have the next column be something called first name. And in there, I'm going to store something called a varchar 255. So that's probably pretty complicated or weird. Varchar 255, it's as if we're writing string, right? So string is the real type, but a string, when we think of strings, we think of something with an arbitrary size, and a database really kind of has to know how big something is. So instead of saying string, we say varchar, which means like variable number of characters. And we say 255 to say how big it can possibly be. So that means we have it's zero index like most things in programming. So that means we have 256 possible bits to store that string. And can anyone tell me what how do we get 256 2 to the power of what?
6 or 8?
It's got to be bigger than that, right?
No, actually, this is right. It's 8.
2 to the power of 8. Okay. So what that means is 2 to the power of 8. See, I don't trust you. I got to search for it. Is 256. Okay. So that means that's an 8-bit string. So that's kind of small, actually. That means as far as I know, if we have, well, that's actually a really good question. Let's look up varchar specifically. Is that a number of bits or bytes? So you generally don't want to have to know too many of the details of how your database works, but your database will be, how your database works will be encapsulated in these types. So right, varchar is a varying number, a varying length character string, and that n represents how many characters. Okay, so what this means is that I can't store a first name greater than 255 characters, but I could store up to 255 characters, which is going to be fine for most first names. However, you might imagine that if you were trying to store, I don't know, like a Dostoevsky novel or something, 255 characters would not be enough. We would have to use a different data type, and I believe the data type we would want there is text. So that's a variable length character string with no limit, but you might think, well, why don't we do everything as text? There's probably a reason around efficiency. It's got to be much more straightforward to store and then retrieve something that has a specific length versus something you don't. But yeah, so that's why we're going to do that varchar there. And then we'll do the same thing for last name. Varchar 255. And then finally, we have this on probation thing, and that's going to be a Boolean, and we know what Booleans are. And then finally, I'm going to close that schema definition, which was in the parentheses, and then all SQL statements end with a semicolon. So if you forget that, it's never going to end. Now we hit enter. Why doesn't it like that? Maybe it wanted it indented. That might be it. So let me try this again. As you can see, it can be a bit finicky. I got to move things out of the way to actually see what I'm doing here.
I don't know. You might not have put the comma at the end of the line.
Can you?
That's a really good point. Yeah, so I was surprised the idea that it would care at all about white space, because usually if something uses parentheses and semicolons. It's not caring about white space, but what I'm going to do now is add commas at the end of all the, so I needed commas there. Otherwise it doesn't know that one column finished and the other started. So if we do this now, how will it feel? We'll see. Okay, it looks like it created the table. Awesome. And now if I hit /D, I should be able to see that I have a table called student. And let's see what the next line is here, because I'll be honest, I forget a lot of my SQL. I don't work especially directly in Postgres too often. So I am curious how I'm gonna now look in this table or add things to it, but this is just some more information about the data type in the schema. So, we might, so I see an integer can represent any number from, -2 to the power 31 to 2 to the power 31. So can represent a pretty big number, but that could run out eventually. We might want to represent a variable number of strings for a relatively short string, less than 255 characters. We have text, we have date, we have timestamp. So interesting that we put this here. I don't know that we show you how to do this immediately, but a schema is not set in stone. You can update a schema over time. But the thing is, all the data that's currently in the database will eventually need to fit this new schema. So that's what we call versioning a database. A database always has a version, and we might say this version is 1 right now. And then if we change the schema, we would say, okay, well, this is version 1.1 or something, to represent that we made a small change. And let's say we said our schema was, we're going to add, an address or something. Well, if we want to do that, we first have to make sure that everything that already exists in that table, currently we have nothing, but if we had a lot in there and it only had ID, first name, last name, on probation, if we wanted to suddenly add an address field, every existing one needs to get an address. And so you got to figure out how you do that. So we don't need to get too into it, but an important point is that when we define something as being like, an integer or varchar 255, generally we could also say whether it accepts null or not, because some things are allowed to have null and other things are not. And if something's not allowed to have null, the idea is that, well, you would have to give a fake address, or you'd have to get an address for everyone in your database if you updated the schema. But otherwise, you could update the schema and say, okay, for now on, everyone has an address, but because we can't guarantee it, because some people were added before that schema update, some people are going to have an address of null. Here we have this idea of the single responsibility principle. This is a general principle for programming in general, and also just for life, which is basically don't mix concerns more than you need to. What this boils down to in general programming is like, if you see yourself repeating something, maybe make a unique function for it. And you don't have to have one function that does everything. You could have, multiple functions that work together, and they each encapsulate, that specific part of the transformation of data you care about. Single responsibility in databases generally means have a different table for different types of data. So right here, I have an example table that represents both a person and their address. And I could have that all in one line. And that would make perfect sense if two people were never going to share an address. But because it's reasonable that two people could share an address, we might want to say, well, we're really dealing with two types of data here. We're dealing with people or students, and we're dealing with addresses. And really, we want to split them up and just connect them with an ID. So instead, I'll say, okay, well, actually, part of that represents the students, part of that represents the addresses. And I break them up and use IDs and foreign keys to make them point to each other. Right, so here I have student, and this is written in a slightly funny way, but I'm saying, okay, addresses start at a certain point. So I see there's duplication there. And I wouldn't want that. So we're basically asking here, yeah, there's some questions here. With this duplication, what are the downsides we can expect if a student changes their name? So who has an idea? Like, let's say a student, we have our student table, and then we have our addresses table, and they both contain this first name and last name data. What happens if we add a new student, and or if a student, let's say Tiana Lowe, her last name, she gets married, I don't know, and her last name is now Tiana Macy's, I don't know. So what is a downside of how we're currently storing things?
You're updating two tables instead of one.
Exactly, yeah. So, I mean, to me, the essential problem here is we don't have a source of truth. As in, we have students, and ID of student 1 represents the student's first and last name, but so does address 4 represent that given student's first and last name. And so there isn't a single source of truth. Instead, there's two sources of truth. And so what happens if they get out of sync with each other? And it almost like it starts to show you itself as a problem where you think like, oh, well, every time I have to update that, I need to update both. Wouldn't it be nice if I just had one place to update it and the other place automatically knew? So what are the alternatives to eliminating this duplication?
Give them a address ID and get rid of the first name and last name in the address table.
Exactly, yeah. So basically we can give each student an address ID. And what that means is that if we know a student's first and last name, or if we're looking at a given student, we can always get their address. Similarly, you can also add a student ID to an address. So if we just add a address ID to the student table, then given a student, you could always look up an address, but it doesn't necessarily work the other way around. So we would really want both if we knew we might be in situations where we would just have an address, but from that, we would want to find out which student was associated. But the core idea is that you would rather have multiple tables representing a specific type of data, and then just use what are called foreign keys to relate one to the other. And notice there's no, when I say like one thing points to another, there's no real fancy thing going on behind the scenes. It's literally that a student would have a column, and that column would hold an address ID, and the address ID would line up directly with a given ID in the addresses table. And by doing that, you just always know where to look. And database rows are similar to arrays in that if you want to get the 44th element, you can just jump right there. And so that's why these IDs are useful, because it means that if I'm already looking at a given student, I've already found the student I care about, it's a constant time operation to get their address. I just look at the address ID and I jump to it on that table. Yeah, and this is exactly it, as in these two students now have an address ID, or the schema for students rather has an address ID column. Each one of these students has a different address ID that points directly to the primary key of the addresses table. So just to clarify, because I've been using these words a lot, when we talk about the ID, we just tend to call it ID, but this is called the primary key. This thing on the leftmost side called ID, primary key. That's the actual canonical, like there's only going to be one of these per person. That's a guarantee the database gives you generally, unless you turn it off. Every person will have, or every student will have, an individual unique ID. Same with addresses. Every address will have an individual unique ID for that table. And then over here, we have the foreign key. Address ID is something that points to something on another table. And while every student or every address, whatever it is, you can only ever have one primary key, you could have 0 to infinite foreign keys, because you might have no foreign keys. It could be that all the information you need about a student is contained in that one table, but you could have as many foreign keys as you want, because it's just a way of pointing to another entry in another table.
Yeah, I have a question.
Yes.
So can we have nested tables?
Not exactly.
Okay.
Instead of nested tables, you have this. As in, you would never have a field within, you would never have a column with the students called like address, and then within that column, an entire table, right? If that's what you're asking, you cannot do that. But the good news is that this idea of tables, so I think this is as good a time as any to talk about the basic idea of a join. So over here, you'll see we have this this example SQL statement, and it involves a join. So let's look at that wherever I have my Excalibur. Okay. So let's say I do have this student table and this address table, right? And we'll just say for right now, this is what we have. We have, you know, a given student, and we have some students and they have these address IDs, and these are the addresses. And let's say I had a SQL statement like this. So I have the SQL statement, which is pretty complex, but it's going to say select star from student left join. We just want to worry about join right now. I'm just going to join types PostgreSQL. This concept of joins can get more complex because there's different types of joins, but we just want the most basic one. Honestly, we're just going to go with left join. I think that's fine. I'll explain the difference, but we're going to say select everything from students. So get everybody that's in students, and then do a left join with, we don't know about enrollments. So I will say, what is it called? This would probably be called addresses or something. Sorry, I'm having a little trouble here. Just to make this, you know, fit our thing, we're going to call this addresses, and, you know, they're both going to be lowercase. So there's addresses and here's students. They're both plural. They're both lowercase. And I'm going to say select everything from students and join it with addresses. And how do we join it? We join it on students dot. Maybe we would say something like join it on student dot address ID is equal to addresses dot ID, and then this where thing is, you know, let's just remove that for a second. Or yeah, so this is going to be our whole statement for a join, and I'm going to, just to make it clear, I'm going to remove these two elements here, and this first one has Jose Delgado, and he points to an address ID of 1. And then who should be the other student that goes here? Let's see who's here, Jody. So I apologize if I spell anyone's name wrong. I'm going to try and look. Mary. So this is the, just a second, something with an ID of 1. Well, you know, let's say he has the same exact birthday, but he's 40 years younger because of how old Jose is. And just to make these line up, this is going to be an address ID of 2. Man, this is, I wish this was not as finicky as it is. Great. So what you could see is that these things, like, you know, this is our students table, and things point to each other, because this 1 is going to point to this address of 1, and this 2 is going to point to this address of 2. And let's make something here, 456 Strange Street. Cool. Having trouble fitting some of this stuff now. City is going to be New York. Just pretend these are strings. It doesn't really matter. 11106. I don't know. So what happens here? We say select star from students. So the first thing that happens is we grab this whole table, right? So sort of internally now, select star from students says, okay, get everything from students. It has this whole table. And then it says left join addresses. So the first thing we're going to do is grab this thing called addresses. We have that now as well. So that lives like here, let's say. And we're saying left join on addresses. So without getting into too much of the specifics, you can have different kinds of joins, and that mostly has to do with whether data is null. So a left join, I believe, means that if anything in this list was null, we just wouldn't include that in the join. Or rather, if anything necessary, like basically if a student had an address underscore ID of null, you wouldn't even try and create something in the resulting table. But we'll just assume this is a join basically, and that because we have all of our data, it's going to be a full join. And so what will happen? Well, I say join them such that we'll join students, which is this one, with addresses, which is this one, but then we have this on. So how do we join them? We join them on this. And what this says is go into the students table, grab the address underscore ID, and match that up with the addresses table where addresses has its own .id. So basically, I'm explicitly saying associate this one over here with this one over here, this two over here with this two over here. And the result is that I actually basically take all of these things and I put them over here. So wherever I had address ID, I now have line 1, city, state, zip code. And so when I return this whole thing, the select star from, this whole thing transformed into a new table. And what we're returning is all of the rows in a table that has, oops, I did that a little wrong. We're returning all of the rows in a table that has everything in here minus these two, and then them pushed together. So like this. This is the final resulting table, basically. If that makes sense. Looks a little ugly probably based on how I did it, but this is the, yeah, that's not bad.
So can you think of joins as linking keys between tables? Because you effectively just took that foreign key from the students table and linked it to the primary key in addresses.
Yeah, so you are right. Joins will just about always have this on statement in which you say associate one key with another. But it's not just that you're associating them, you're actually creating a new table temporarily. It doesn't last at all. But for the sake of this query, we created a new table that contained all of those columns. So that when it returns, we have something with all of those columns. We could possibly show this more easily by actually adding things to Postgres directly. I often forget exactly how to do that. Some of you might remember your Postgres better than I do, but right, insert into, so maybe, you know, this is how we might do it. You say insert into, you say the table you want to insert into, you say the columns you're trying to add to, and then all the new entries you want to add into that database. So I guess we can try this for the sake of showing this actually working. So I have my, gotta move things out of the way again. So I have my students table, right? And so just remembering my exact stuff, I say insert into the students table and then it's schema. So insert into, and then I say students, right? And I already have students. And what does a student look like again? It has I just care about the names of the things now, an ID, a first name, a last name. Let's forget about on probation. Let's just give it an address ID. So you'll notice I can give it the address ID before we even have an address table. It's just a number. So I'm going to insert into there. And then the next thing I write is values. Does it understand? Yeah. So, and then what are my values? I'm going to have individual values that look like this, which are, let's say we had an ID of 0, a first name of A, a last name of B, and an address ID of, let's say 1. And then I actually need to put a comma after that probably. Just make sure I'm getting this right. And then we'll do it again. Oops, it won't let me do that. So I'm going to give it an ID of 1, a first name of C, a last name of D, and then an address ID of 2. I'm realizing this is going to break because this doesn't fit our current schema. So maybe this is a fool's errand. But you'll notice at least this is why SQL is useful, because it's telling us, hey, you didn't match what we expected. Might be too complex to get into now. Like I don't actually, off the top of my head, I don't know how I update the schema. I might just have to delete a table and create a new table. Probably more work than it's worth right now. So we'll just, I guess I'll just ask, how much sense does this make that you can use joins to create a new table out of 2 existing tables, and then that's the data you're going to get back, not, you know, the, yeah. Does the basic idea of joining make sense? I see a thumbs up. Okay. Cool. So as we mentioned, those columns, you know, you give them a type. But part of giving them a type is explicitly saying whether something can be null or not. And this helps with the idea of data integrity, because as you saw, I just tried to add something to the database, and I tried to add to a column that didn't exist, and it didn't let me. But just in the same way, what if you add a new row to your database, but you're completely missing a certain column? Well, that data might not really make sense without that column. So let's say we had users here, you know, we have an ID, an email, and a password. What if we had an ID and an email, but we didn't have their password? It might not be a very useful schema at that point. So there's different constraints you can give, like one of them being not null, but another one is unique. So in this case, we're saying, okay, we have a problem here because we have this user database, but what we should have said in the schema is that emails have to be unique. No 2 emails can be the same. Just like an ID, they're supposed to be totally unique within that table. So I'll be honest, these slides are making me a little crazy. I don't know why they're not showing an example of it. But if we were to define our schema, we should have this keyword unique. So if we were to define a schema, we might create a table. And if we created a table, it's going to take something that looks like this. Yeah, and exactly. One of the constraints would be unique. So I could write something like, you know, let's say I would have like email, and then maybe for data type, I would have, you know, varchar 255, because we don't expect the email to be longer than that. But then right after that, I could write unique. So let's try that. I'm going to create a new table called users. So create table users. Let's see if I'm getting this right. I'm going to open parentheses, enter. I'm going to give it an ID because everything has an ID. And I believe that by default IDs get unique. I'm not positive, but we'll just assume right now IDs get a few IDs by default, I believe get unique, which is over here, and they get primary key. And the important part about primary key is that every time you add something to the table, primary key goes up and it never goes down. So you're always going to have that new ID. But right, we're going to have an ID of integer, and then we're going to have an email, and we're going to say that email is a varchar 255, but then importantly, we're going to say unique. There can't be more than one of these. And yeah, I guess after that, we would have password, and we don't really care about password. I wonder if there's a specific way to store them in SQL. So I wonder if there is a SQL data type for passwords. There probably is. Maybe not. Okay, well, by default, I'm just going to save this password then, and we're saving it exactly as it is. We're not hiding it in any sort of way. But maybe I'll say you need to have a password. So your password cannot be null. So did I do that right? Not null like that? Yes. Okay, and then this is going to be my entire schema. So I'm going to close that parentheses and end with a semicolon. And now I have this table called users. So I have my table called users, right? And this is what it looks like right now. This is just showing me its schema. You don't have to worry about too many of the defaults here, but it is saying that a password can't be null, and that, you know, there's this issue, or there's this way by which an email is, you know, it has a constraint that it's unique. So whoever I was talking to earlier about the idea that you could have a way, like if you wanted to check things against each other to make sure, like let's say you wanted to not have to look through every single, I forget exactly what the conversation was, but I was looking for a specific word, and that word is index. And index is a pre-computed thing that lets you easily look up like uniqueness, for example, between keys. But you don't really need to know those details yourself. So now I'm going to say insert into users, and let me make sure I'm doing this right. Let's see, insert, it's got to be somewhere. There we go, insert. So basically I could say insert into the columns I care about and the values. So let's see if I can do this. We're going to say the columns I care about. So watch, I'm not going to say ID because I think it'll just give me the ID automatically. I'll just say email and password. So I'll say email, comma, password, and then I'll say values, and those values will be, make sure my syntax is right. Yep. My values are going to be for the email. Let's just use those ones right there. james@example.com. And then the second one will be just, you know, PEA098. Okay, that's their password. And I hit enter. And it's a little odd that it's saying insert 01, but that's telling me it inserted something successfully. And so if I now want to see that table again, I see this is just showing me the schema for the table. But, you know, I could say select star from users, and that's going to show me my whole table, right? Cool. I see my ID is empty, so that's not good. I should have given it a value. But let's say I try and insert into this. Okay, we're going to change this a little. I'm going to give it the ID explicitly. Okay, so I'm going to try and do this, right? And I'm saying, okay, well, the ID is going to be 1, let's say. But I said that my email has to be unique, right? So if I do this now, what happens? Cool. It says we have an error, duplicate keys, violates unique constraint. So it actually knows. And similarly, we had that not null thing. So if I try this again and I'll say not James, but Sally, I said this can't be null, right? So if I leave that out, well, if I just leave it out, I wonder what happens. Right, it's a little confused because it's saying you don't have enough values to match your columns. But let's say I explicitly wrote null here. I think also if I just didn't include the password, it's going to say, sorry, that row contains null and we have a not null constraint. So those are the constraints. The idea of a constraint is that you can't put data into it, because you probably noticed by now already, based on what I've done, it's easier. It's pretty straightforward to add something. It's a little harder to change something that's already in there. So if I mess up in some way and I add some data and that data doesn't really make sense, I could cause some problems for myself. So ideally I define my schema up front so that I don't run into those problems, and then I don't have to like later fix the entire database. All right, so that's the basic idea of constraints as it relates to this idea of data integrity. So any questions there before we move on to queries?
Yeah, so how did it know that it was a primary key for the ID? Did you specify that, or do you treat that as a primary key?
So I didn't specify anything, and I think that's the reason why, if you notice here, I said insert, where is it? Yeah, I said insert into users, and I didn't give it the ID, right? And then you'll notice it had no ID here. And that's, I believe, because I made a bad schema. So if I go back here, I think there's something called, there's a way to, there must be a way to update the entire schema. But I suppose for simplicity, I will just delete the table and then start over. So what was that? Drop table. So that's how you get rid of an existing table. You just say drop table. So I'm going to drop table users. And after that's done, if I try and say /D, you'll see I have something called students. I don't have something called users. So I'm going to go back to where I was back a while ago. I'm going to create this table called users. How about that? And over here, I just set an ID of integer, right? Well, it sounds like, based on what I read. So if I look here at, not here, if I look here, at some point we were looking at this idea of constraints. So we have the not null constraint. That's not where I want it. Right, so we have unique, not null, but one of the other thing we have is primary key. And I see that it's using serial for the ID. I'm not positive what serial, I mean, serial would just be another data type, but it looks like we have this primary key thing. As you see, there's a lot of information here. So like, when learning this stuff, and even when using it later, you'll probably do a lot of Googling, or not Googling, but like using these sites, because I'm just trying to look right now, how do I define a schema? What's the possible stuff that can go in there? And it's kind of hard to see it all in one place. Where might it be?
I think that was the answer to my question, where it was serial primary keys. Like when you're creating that schema, like how do you do it?
Yeah,
I guess I didn't know that part. Yeah, that's more of the question I had.
okay, got it. Yeah, well, I think the point I wanted to make is that if I actually update this to say, okay, it's not an integer, but it's a serial, which probably means, it's a number, but it's only 0 or positive, and it can go forever. And then I say primary key. At this point, I believe if I hit enter and then I try and insert something into here, if at this point I try and say, I just want to insert an email and a password, and I hit enter, Okay, that worked. And now if I want to see my table, or rather I want to see, I want to grab everything in my table, you'll see it has an ID of 1 now. And that's because we said primary key. It knows, okay, well, that always is going to have a value, and I'll just increment by 1. So if I were to once again try and add something to it, this won't work because it would be the same. And there's a constraint on there. But if I say Sally and I hit enter, that also works. And now when I say select from, that has an ID of 2. So I just wanted to show that. But do you feel that